for our this independent study course, CS5880, I want to choose the big topic, data science topic. Okay. Then, so let me give you the general goal for this class. Okay, yeah. So the goal is we extract useful features right, from given set of data. Set of data. Later, let me explain this data part. Okay, yeah. Through data manipulation. Yeah. So I will spend a lot of time to talk about data manipulation. Yeah. It could be very complicated. Yeah. So we will, step by step, learn how to do different types of operations. Yeah. All right. And yeah, so that is the goal. All right. Yeah. Then the data format. Let me talk about the data format we work on. Yeah. Yeah. The general format. Yeah. It is a sequence of data points. Yeah. If I use math representation, I like to use this one. A pair of curly braces as a sequence. And the points, I use X coordinate and the Y coordinate. Yeah. With subscript J from 0 to N. So that is the general expression, a sequence of data points. Yeah. Each point on a plane. Yeah. So X, Y coordinate. Yeah. So we study this general data format. Yeah. All right. And we may like to draw, if we draw graphs on a plane, X, Y coordinate. Yeah. So we may have, data points spread, yeah, yeah, many different ways. Yeah, you can imagine. So this is X1, Y1. Yeah, the general case. This one XJ, YJ, and let's say this one, the last one, XN, YN. Yeah. Like that. Yeah. And here, yeah, we like to have the condition because the X coordinates corresponds to X direction locations of the points. Yeah. So that's the XJ part. XJ part, locations. Yeah. And the Y coordinates, Y part. Y part, that's the value part, data values, values of the data, yeah, locations of the data points. Yeah. All right, so that's our typical setting of data. Yeah. All right. So that's the first concept. Second, I like to talk about another concept. Yeah. Yeah. So let me put a number. Number one, data format. Number two, yeah. Number two, we consider a special case of data. Yeah. A special case of data. Number one, that's the general case. How special it is, yeah. Still, our general form, xj, yj, the sequence, yeah, it takes a special format. That is, so what's that special format? Yeah, like that, like this. Tj, f of tj. This format. Yeah. So this special format here, let me explain how special it is. Yeah. First, this f of t, we call it, yeah, a time series. T represents time, okay? So it is a function of time, okay? Its value changes with time as the variable, yeah. So we call it time series. And it is this function, it is a continuous function. So you know continuous function, right? Yeah, so it's a graph, continuous, okay? No breaking point, continuous, okay? Yeah, no breaking point, yeah. Do not like that. You have a jump. Yeah, this is not continuous function. So you know, broken somewhere, yeah. So not continuous, yeah. And this is continuous, yeah. All right. So the time series, then the x coordinate represents time. Yeah. So then y coordinates a function of time. Yeah. Then this time sequence, yeah, time sequence. Okay, yeah. And f of tj, so we called sample values. Sample values, because we take samples from the time series functions. Yeah. Or we call time series sampled at these time locations. Yeah. Yeah. All right. So this is a special case. Yeah. Because why I talk about this special case? Because this special type of data corresponds to signal processing. signal processing. It is one important type of data processing, signal processing. Signal processing usually 1D signal, 1D signal. So that's the voice file. Okay. 2D signal. Image files. And a 3D signal. Video files. Yeah, so very important. Yeah. All right, so this type of data, very important. Yeah. All right, and here let me give you some background about signal processing a little bit. Yeah, because this independent study, I do not plan to go that direction, signal processing direction. So we work on the non-signal data. So there is, no time involved. Actually, because we are working on the general form, the time case, it's a special case. Yeah. So when we work, we cover that. Yeah, but actually, we work on more general form. Yeah. All right. Yeah, but I need to give you some background on this one because we may need to use background from the signal case. Yeah. All right. So one background I like to give you is digital filters. Digital filters. In signal processing, we do operations with digital filters frequently. Yeah, so let me give you this background. So what's a digital filter? So digital filter is just usually a sequence of numbers, okay? Like this sequence of numbers. This sequence could be finite or infinite. Yeah, but most of the time we work on the finite filters, right? Only in some very special situation we may use the infinite filters. Yeah, but here let's assume we only consider finite filters here. Yeah, and let me give you a simple example of the filters. One filter, one digital filter. Okay. Here, let's assume our filter is these three numbers: 1/4, 1/2, 1/4. These three numbers. Yeah. All right. Then, how to apply filters? How to apply filter on a digital signal? Yeah. Here's the question. Yeah. How to apply a filter on a signal. Let me just write signal. Okay, yeah. So this question we call the filtering. filtering. Yeah. So let me define this filtering operation. Okay, yeah. Filtering operation. Yeah. All right. The filtering operation. Okay. Yeah. Here I define convolution operation. Okay. All right. All right, the general convolution operation definition is like this. Okay, yeah. Here, suppose when we start, we have a sequence of data. Okay, yeah, or signal. Yeah, all right, yeah, and we apply a digital filter here. This H filter, yeah, and the output, yeah, the input X sequence, the input, output Y sequence, output, yeah, and the operation is convolution, and its definition is Yj equals summation. Okay, yeah. Hk, yeah, times xj minus k. Okay, yeah. The summation. Okay, that's the definition of convolution. This process we call it filtering, digital filtering. Yeah. So it's a basic operation in signal processing. Yeah. With different filters, when we do digital filtering, we can do many applications. Okay, yeah. Here I do not go very deep. Yeah. So we only need to use some background. We need to use digital filtering background, yeah, in our project. Yeah. Here, let me give you an example, yeah, because in our example I talked about in the previous slide, suppose our filters is this one. Yeah. How do we apply filters on a signal? Yeah. Let me show you this. Here, let me just use the first number. I call it H -1. Okay. Second one, H0. The center, I put 0. Okay. Yeah. The third, H1. Yeah. Then I use the convolution formula, definition formula. So Yj for this filter, yeah. So it equals H -1 times xj +1, because k equals -1, j minus k, so j +1. When h equals 0, subscript of x equals j. And the third term, h1 j minus 1. Okay, yeah. So if we plug in the numbers, 1/4 x j minus 1 plus 2xj plus xj +1. Yeah. So you can see the specific filtering operation, we just do this kind of simple operations. Yeah. So not very difficult. Okay. Yeah, not very difficult. Yeah. Yeah. So that's the digital filtering. Yeah. Yeah. Later, we will do more discussion when we need it. Yeah. Here, I just want to stop here. Yeah. Later, when we go further, so you will get different filters. Yeah. You will learn different filters. Typically, there are high pass filters, and low pass filters. Yeah. Later, when we need to use those kind of filters, then I talk about that. What's the meaning? Yeah. Yeah. So today I do not need to, go too far. Yeah. Along this direction. Yeah. All right. So that's the digital filtering concept. All right. So next, related to filtering, there is another concept, also very important, and we need to use it in our discussion. Yeah. So that concept is frequency of signals. This concept, frequency of signals. All right. Yeah. So here I like to draw a graph of two different cases for the signal. So one like this kind of signal, all right? Another type is like this. Waveform, all right? Waveform here, you can see their frequencies are different. These two signals, they have different frequencies. Yeah. This one, we call high frequency. If we compare high frequency, the frequency higher. Yeah. This one, low frequency. Yeah. Why we like to consider high frequency, low frequency? Usually, a signal, when we have a signal, we like to decompose a signal into high frequency component and a low frequency component. Okay? Yeah. If we can, divide or decompose a signal into different frequencies, then when we do applications, we can work on different frequencies. We can do different operations on different frequencies. Yeah, so that's the usual way we do signal processing. Yeah. We need to do decomposition first. We need to do decomposition first. All right. After decomposition, then we do manipulation on different frequency components. Yeah. After that, then we combine the, components of different frequencies. we combine, yeah. So we recover the signal. So that's the typical procedure for signal processing. Yeah. All right. So here, let me write a general expression of signal decomposition. Yeah. Signal decomposition. All right. Yeah. Signal, but later we will generalize to data decomposition, general data decomposition. Okay. Yeah. Here, the signal decomposition. So given a signal, we know this is the given signal. We like to decompose this signal into different components. Each component has its own frequency. Yeah. So like F1, T sub j, F2, T sub j, Fk, T sub j. Okay, yeah. So you can see each one corresponds to one of the components. Okay, yeah. How to do decompositions? Yeah. We apply digital filters. Yeah. For component 1, we apply filter 1. Component 2, we apply filter 2, and so on. Okay, yeah. So component 1, we apply digital filter H1. Okay. Component 2, we apply filter H2. Component K, we apply filter HK. Okay, so straightforward way. Yeah. So that's the signal decomposition concept. All right. Yeah. And for applications, yeah. All right. So here, let me give you the general applications for signal processing. What do we do? Signal processing. Okay. We do various operations okay, on different signal components. All right, yeah. So that's what we do for a typical signal processing application. Yeah. All right. So with this background, next we need to look at the data representation. Now we need to work on data, okay? The general data, yeah. So we need to consider data representation. Okay, yeah, all right. Here, we start with a sequence of data points. So that's our general data. All right, yeah, in this way. Then we like to represent this data or data representation. We call it modeling, okay? we try to find a suitable model for our data. So data modeling, okay, so suitable model. Yeah. Because if you do not do this step, data representation, data modeling, yeah, it's very hard to apply mathematical tools on data. So here, why we do this part, the goal of this step, the goal, okay, yeah, we need apply various mathematical tools on the data points. All right, yeah. Without model, without representation, we cannot apply any mathematical tool on it directly. Yeah, it's hard. Yeah. Okay. So we need to find a mathematical friendly way. Yeah. The representation should be friendly to math. All right. Yeah. So what's that? So what do we mean friendly to math? Yeah. So what do we need to do? Yeah. Find a good. Later, I will describe what's the meaning of this good, double quotes good, special meaning here. A good continuous, continuous, yeah. Function f of t. Originally, there is no such function. Yeah, so here we need to find that function. The function does not exist originally, okay? No such function. So here we find that function. So that step we call the modeling, okay? Yeah, you need to find it, a suitable function, yeah. F of t such that f of xj equals yj, okay? Yeah. So there is a continuous function that connect xj and yj. All right, yeah. So this step, this is the data representation step or the modeling step. All right, yeah. So, and why do that? This is the reason to do that. Because if we have this nice function, yeah, good, yeah, that means it should have some good properties. Good. So then we can apply many mathematical tools. All right, yeah. So that's the, the reason we do this data representation step, yeah, modeling step. Yeah. All right, yeah. Okay, yeah. So here you may ask me what kind of mathematical tools. Here, let me give you some simple examples. Okay, for example, you may like to find derivatives. Okay, yeah, integrals, right? Yeah, etc. Yeah. Think about if you do not have a good function to represent this set of data, how can you apply derivatives, right? How can you apply integrals? many mathematical tools, powerful mathematical tools. You can never use any such powerful tool, right? But if you have a good representation, then so many powerful tools available in math we can apply, okay? So we can do large number of operations. Think about that, how good it is, okay? Yeah, and currently, you don't worry about all those tools. We can find, Python function, many libraries, we can find those tools. Yeah. But you need to have background first, right? Yeah. If you don't have the background, you may not know which function, why you need to do that, right? So here I'll give you the background, because later, after you get ready for your preparation, so then we can apply some Python functions to do data processing. Okay, yeah. All right, let me see. The next step, yeah, here already, 412, yeah. On my side, I have a few items, but I promise you in our first meeting, I do not use too much time. Let me stop here because I have about 5 items left. And these 5 items are very important. So let me leave these 5 items next time. Yeah. So next time, when I talk about these 5 items, I will explain a little more details. So yeah, because those 5 items, so that prepare you for the project quickly. Yeah, the project rely on those 5 items. All right, yeah. That's what we need to do today. Yeah. Yeah.
Sure, Professor. Thank you.
Yeah. After this, I will, post the video on YouTube, then put a page in our independent study. Yeah.
Okay.
Canvas page. You will see it. After I post it, I will send you an announcement. Yeah. So if you need, you can take a look. Yeah. Yeah. All right. So that's it. Yeah. Yeah.
All right, Professor.